Okay, now we want to vertically shift a graph. So here's a graph of a power function, y equals x to the p. It looks different than the power function we used in the preceding where we were doing a vertical stretch, but there's no particular reason why. I just want to use a little variety in the power functions. Okay, so the vertical shift of this power function displaces each y value according to this arrow by this much in this direction. So we could put a number on that, but we don't have a scale on this graph. So I'm just wanting to displace each y value by this much. Well, that means that, for example, you can see, I think you can pretty much see the y values that I used to construct the graph. I don't have to use these particular y values, but or these particular points. I could use any set of points on the graph, but it's convenient to go ahead and use these. So that means I'm going to take the y value here and I'm going to displace it in this direction by this much, which is going to put me here, and I'm going to actually draw that arrow and indicate that new point. And then I'm going to do the same thing here. Okay, and I draw the arrow and indicate the point. Then again here, it's going to put me about here, and I'll draw the arrow, indicate that point. Again here, I think that's going to put me about here. Draw the arrow and indicate the point, and looks like that arrow's a little longer than this one. It's about the same. Okay, and then here. And I'll draw the arrow, but I'll kind of interrupt it for my labeling. But we see now that we have a set of new points, and we can sketch a curve passing through these points. I made that point a little too high, but we get the idea. Okay. Also, we could extend the y-axis. So that each point on this curve is this much higher than each point on the original curve. Now, the displacement doesn't necessarily have to be upward. What if the displacement was downward? Well, then every point would go that much lower. Some of the points would obviously then be carried to points lower than the x-axis, and that's perfectly all right. So, if our arrow represents a vertical displacement K, and what is the equation for our new function, which we'll call the function g of x. Okay, so that's the first question we want to answer. A couple of other questions. Is g of x a power function? Okay. Is g of x a power function? Is there, I'll say, does there exist, question mark, that means does there exist a displacement k such that g of x is a power function. Now, of course, if g of x is indeed a power function, then your answer to this question is yeah, because k could be any number, it means g of x is always a power function. So certainly there exists a k, just pick any k. And I guess I should precede this statement with the statement that g of x is a generalized power function. But the question is g of x strictly a power function? And what's the criterion for a power function? Well, the criterion for a power function is that g of x would have to equal x to some power, not necessarily the same power, but maybe. Or alternatively, and the graphical test that's equivalent to saying this is that anytime x doubles, y has to change by the same factor. So you have a constant y factor associated with every doubling of x. So we can answer the question, is g of x a power function, based on that geometrical equivalence, that geometrical definition of a power function. So those are questions that we should answer. Is g of x a power function? Can g of x even be a power function? Maybe it always is, maybe it never is, maybe it sometimes is.